When nature contaminates Winnie the Pooh's secret stash with neurotoxins, you get mad honey. This substance was used as a dubious cure for insanity, a biological weapon, or simply a nice skin softener. More recently, it has seen broader interest in its hallucinogenic properties, which obviously cannot be recommended by this channel. In this interdisciplinary video, we will discuss mad honey toxins and other devilish molecules from several angles. Among many nice learnings, we'll discover how eating toxic fugu fish might theoretically combat mad honey intoxication, how innovative non-opioid painkiller drugs work, and how we can approach the chemical synthesis of the complex toxin Kalmanol. This natural product originates from a small, colorful garden shrub native to North America. It might look cute, but don't be fooled. It's called lamb kill or sheep poison for a reason. These plants are poisonous because they contain toxic natural products. Kalmanol is one of them and was first discovered in 1989 through a rather uneventful isolation. Take some kilograms of dried leaves, run repeated column chromatography, try to find a few milligrams of unknown compounds, you know the drill. This sneaky toxin is just 0.001% of dry plant weight, but actually this isn't as bad as other natural products that we've seen in previous videos. Structurally, Kalmanol represents an interesting variation on the molecular framework of the better known Grayanotoxins. If you compare the architectures, you'll realize that the carbon ring connectivity is slightly different, with Kalmanol featuring an expanded central ring. Grayanotoxins occur in many other plants as well, and they are the primary culprits behind the strange effects of mad honey. Let's check out my favorite high-impact journal, the Balkan Medical Journal. The effects of grayanotoxins were recognized already more than 2000 years ago by Xenophon, a student of Socrates and military commander. In addition to being among the first to describe military tactics in writing, he documented an accidental encounter with mad honey. As his thousands of troops were marching through what is modern Turkey, they found a quote, astonishing number of beehives. Little did they know that the honey was contaminated with grayanotoxin, so it took them 3 full days to recover enough to continue their march. The use of mad honey by natives surely dates back even further, but more interesting is what happened in more recent history. Xenophon's troops were pretty lucky because their enemies could not capitalize on their incapacitation. Few centuries later, but still around the same block, the army of the Roman general Pompey had a much worse trip. Pun intended. Basically, their enemies utterly outplayed them by using mad honey as an early biological weapon. Historians don't know which exact units of manpower measurement the ancient accounts refer to, so Roman losses due to the mad honey warfare range from 500 up to 1,800 men. As we all know, humans are proficient at messing around with toxic substances. If not used to kill people, it was used to heal them, or that's at least what they thought. The alleged healing properties ranged from instantaneously curing epilepsy, treating sunburn, or quote, softening the skin of females. Due to its hallucinogenic effects, mad honey was and still is used as a recreational drug. There has been a recent surge in internet attention, but the use of mad honey cannot be recommended because these are literal toxins that can have poisonous effects and even lead to severe heart complications. You see, biochemically, the grayanotoxins and their relatives like Kalmanol interfere with so-called voltage-gated sodium ion channels which sit in the membranes of various cells like neurons or heart and skeletal muscle cells. These channels are main players in electrical signaling that is based on changes in the concentration of charged ions. There are various types of channels, but to not derail the video, we just need to know that they can be open or closed. This makes sense because if there would only be an open state, the cells would not be able to identify or propagate signals. It would be like trying to send a SOS signal, but you can't flick the light on and off. Normal channels turn inactive after sending a signal, but grayanotoxins can bind to the channels and trap them in their active form. This disrupts the natural ion equilibrium, messes up signaling pathways, and ultimately leads to toxic effects in the cardiovascular or central nervous system. Many other famous natural product toxins also bind to sodium ion channels. However, because they bind to different parts of the channel, they can have different effects. For example, batrachotoxin from the poison dart frog binds to the site too, just like grayanotoxin, and leads to similar effects. However, conotoxin from cone snails or tetrodotoxin from pufferfish and other marine animals bind to site 1. Instead of overactivation, their binding does the opposite. They block the sodium ion channels, preventing signals from being transmitted altogether. In the worst case, this leads to paralysis and respiratory failure. Let's briefly look at the impact of the sodium channel overactivation on the heart. The effects of our toxins were already investigated half a century ago. The experimentals are a bit brutal as functional heart tissue was required from somewhere. In this case, guinea pigs. In the chart on the right, you can see that exposure to grayanotoxins reduces the ability of the heart to contract over time. The two different lines correspond to two related grayanotoxins, and clearly both of them are toxic. We can even connect the dots again with the fugu-toxin tetrodotoxin. The same study nicely showed that this different channel binder has an antagonistic or opposite mechanism that can reverse grayanotoxin-induced arrhythmia. Simply put, the heart cells start at normal, then go crazy after grayanotoxin exposure, and finally calm down as the tetrodotoxin inactivation of sodium channels starts to compensate the grayanotoxin overactivation. Unless you have a pufferfish ready and precisely inject yourself with the right amount of tetrodotoxin to perfectly equilibrate your body without any harm, you shouldn't try mad honey because the risk-benefit profile is quite bad, even if you are clinically insane or have particularly dry skin. Chemists spend considerable resources on trying to make toxins that occur in nature in the lab. But why? Well, by accessing larger quantities of the sneaky natural products than we can isolate, we can more comprehensively study their mechanisms and the underlying biological target. In the unlikely but the best case, natural products turn into medicines or inform adjacent drug discovery campaigns. Total synthesis also advances chemistry as a whole by catalyzing the discovery of new reactions or synthetic strategies that may have broader application to other molecules. It might seem silly, but one of the main reasons is simply professors flexing their chemical prowess and raking in more impressive publications. There are other reasons, like being able to conclusively confirm a potentially debated structure or providing chemists with great training, but these are more secondary. On the other hand, synthesis for the sake of synthesis is a low-value activity, as we are increasingly saturating what we can learn from synthetic endeavors. Nowadays, it's considered that virtually any structure can be made in the lab, assuming we have enough time and bodies to throw at it. The literally biggest example for this is madotoxin, yet another sodium ion channel binder. This gigantic, ultra-toxic marine natural product was pursued by Nicolau and co-workers over years. After extensive work on the individual fragments of the molecule, the project was stopped given a lack of funding, but probably could have been completed with more resources. Because most total syntheses do not contribute to meaningful breakthroughs, you can argue that these resources should be redeployed to other research. Nicolau's quote about the fragments of madotoxin nicely highlights our next point, the interdependence of structure and activity. We've mentioned that our main character Kalmanol is a cousin of Grayanotoxin. You shouldn't be surprised that they exhibit similar effects on the heart, but there is interesting evidence that structural variations in the broader family can abolish toxicity. Kalmanol itself is less potent than Grayanotoxin, but we don't know why or if the decreased toxicity might even be a helpful property. For Grayanotoxin, chemists already explored structure-activity relationships back in the 80s, so before Kalmanol was isolated. Replicating something similar for this molecule could help us find unexpected or maybe selective effects against these ion channels. You see, targeting voltage-gated sodium channels holds promise because they play key roles in many different diseases with wide expression across tissues. Several sodium channel blockers have already been approved as anesthetic or antiarrhythmic drugs to regulate the heartbeat or manage blood pressure. But because there are different subtypes of channels, selective effects could unlock additional therapeutic avenues. Over the last year, we've seen clear clinical progress of selective inhibition of the voltage-gated sodium channel 1.8. This channel is found in the peripheral nervous system and plays a key role in pain signaling. By blocking the channel, investigational drugs aim to suppress neuron activity and provide pain relief. Because NaV 1.8 is not expressed in the brain, it is not associated with addiction. Such drugs would be a welcome alternative to opioid painkillers for millions of patients, but you'll know that drug development is rarely a home run. This most advanced inhibitor showed good pain suppression in acute pain after certain surgeries in a large clinical trial. Visually, you can see that the reduction in pain on the y-axis is lower compared to the black placebo control. The US FDA might approve the molecule by end of January 25 in acute pain, but very recent data shows that broadening the use to other pain states might be more challenging. On the right, you can see data on the pain response in neurological pain coming from spinal compression and inflammation in the lower back. Despite the significant reduction overall, the clinical trial did not see any separation from the placebo curve, which makes it hard to tell if the drug has a special effect or not. There would be a lot to discuss here, but let me just highlight that placebo analgesia is a well-documented phenomenon. Because patients in the blinded clinical trial expect that they might be on the active drug, their pain can decrease significantly even if they're just taking a placebo pill. This isn't the only complication. Patients are most motivated to enroll in clinical trials when their pain is very severe. But because pain can change over time, it can decrease on its own, if you will. All in all, this is definitely an interesting field. Let me briefly thank my amazing channel supporters and also you for your interest. If you like this type of content, please do me a favor and leave a like, comment, and also subscribe if you haven't already. Beware, the next section is specialist content, so don't expect to understand it all. We'll now focus on one synthesis of Kalmanol published in 2024. This one came 1 year after the first successful one in 2023, which means that 3 decades have passed since initial attempts in the 1990s to finally see success. If you're a student or synthesis enthusiast, pause the video and think about potential retrosynthetic approaches yourself. We're not going to talk about all the options, but maybe you're eyeing that central 8-membered ring. Disconnecting this one seems like a strategically smart idea. It is decorated with several hydroxyl groups, but one suggestion you might propose is to make the 1,2-diol through a pinacol coupling. For example, throwing samarium iodide on the aldehyde could generate a kettle radical species that can link up intramolecularly with the ketone. Planning chemistry on paper is very easy compared to grappling with the molecular realities in the lab. For example, medium-sized rings like the cyclooctane can be tricky targets because they carry significant strain energy and can exhibit very complicated conformations, making stereo control during synthesis challenging. In simple words, what might work in theory does not necessarily work in practice, and rarely are chemists successful with their first attempt. This again makes it complicated for students, as chemists often do not disclose all of their hardships or logic. Looking at the publication of the 2024 synthesis of Kalmanol, a very specific intermediate simply falls out of the sky. This can seem pretty random. The authors supposedly already started with this specific retrosynthetic design, which requires several selective reactions to be successful. Some of them are obvious, like making a tertiary alcohol from the corresponding ketone. On the other hand, the stereoselective introduction of a hydroxyl group seems less intuitive. It's simply that after some curveballs and roadblocks, this approach turned out to work. So don't feel bad if you're reading such papers and not getting why something was quote-unquote planned in a certain way. For these reasons, we will not dwell on the retrosynthesis in too much detail. However, two disconnections are key. The cyclooctane was indeed the first ring to be disconnected, specifically through a ring-closing metathesis reaction. This will require two vinyl groups that can be added through 1,2 and 1,4 carbonyl additions. Linking the two halves might be accomplished through a Grignard addition, one of the first named reactions students learn about. This intermediate looks complex by itself, but fortunately, there's a simple literature precedent to make it. This is because the reaction of cycloocta-1,5-diene with a palladium 2 salt and lead tetraacetate nicely forms the 5,5 fused ring system. The stereochemistry originates from two key steps. After initial coordination of the pi complex, a trans-oxypalladation reaction gives a palladium carbon bond that can insert into the other bond in a second step. This achieves the transannular ring closure. We don't really care about the stereochemistry of the acetates, but the selectivity arises from a SN2 displacement of palladium, which proceeds with inversion of configuration. The acetates are removed through hydrolysis and we get our racemic product with both hydrogens on the same side. Because the chemists wanted to achieve an asymmetric total synthesis with just one enantiomer, they had to separate this racemate. A lipase enzyme can help because it preferentially reacts with just one enantiomer due to its own chirality. This simple reaction gives us a nice 98% enantiomeric excess. It just takes 15 days for full conversion. I mentioned that we don't care about the stereochemistry of the hydroxyl groups here because they were simply oxidized to the carbonyls next. One of them was protected as the ketal because we only need it in its ketone form later on. Remember the Grignard reaction that we were planning for? To get to our target aldehyde, we need to add one more carbon in the correct oxidation state to the ketone. Here we can use a trick with the Wittig reaction, another transformation in every student's toolkit. By using the phosphonium ylide with a methoxy group, we incorporate a hidden carbonyl which we can remove in a second step with acid. The authors encountered a slight issue because the protonation occurred from the wrong side. Luckily, adding DBU triggered epimerization at this alpha position to give the desired configuration with a 10:1 preference. What about the Grignard reagent? This reactive nucleophile can be made through a halogen metal exchange of an activated precursor. We can get there in 4 steps from what is a common starting material in terpenoid total syntheses. Like in our first fragment, we need an enantioselective step to achieve the asymmetric synthesis. Here it's a simple CBS reduction of the ketone, where picking the right enantiomer of the catalyst gives us a chiral alcohol in 86% enantiomeric excess. To not interfere during the synthesis, the alcohol was protected with a TBS group. The remaining ketone was desaturated, and finally, an iodine was introduced at the most activated alpha position. Easy come, easy go. The iodide easily turns into the Grignard species that adds to the aldehyde in a nucleophilic addition. If you're an advanced viewer, you might be wondering about the diastereoselectivity. We'll not explain it here in detail, but basically the major product is not the one that we would expect considering sterics. Instead, it looks like the ketal protecting group can coordinate to the Grignard reagent and direct the addition from the more crowded phase, giving the so-called anti-Felkin-An product. Now that we've linked one side of the cyclooctane, we have to close it on the other side by adding vinyl groups for the ring-closing metathesis reaction. The first one was introduced through a 1,2 addition. The diastereoselectivity in this reaction was not surprising, as the nucleophile exclusively added opposite to the bulky TBS group. To avoid separate experimental steps, they immediately protected the secondary alcohol as an acetate. This one obviously reacts faster than the tertiary alcohol, which can be left unprotected. Next, they removed the ketal to reveal the ketone. To introduce the second vinyl group, they first prepared the enone with the help of benzene, seleninic anhydride. Just like selenium dioxide, this reagent desaturates the ketone through a syn elimination process. Then a conjugate addition gave the ring-closing metathesis precursor. To shift the preference towards 1,4 as opposed to 1,2 addition to the carbonyl, they added a copper catalyst to the Grignard reagent. By the way, if you want more practice with organic chemistry, then check out my website for some more exercises. Let me know if these problems are interesting or helpful so that I can work on additional ones. The ring closure was non-trivial, so I was not lying when I told you that real implementation of reactions can be difficult and that 8-membered rings can be strained. This is also a nice lesson that sometimes missing a protecting group can be very helpful. Here the authors saw that protecting the C5-hydroxyl group shut off the reactivity towards metathesis. With this step they nicely completed the carbon framework, but some work was still needed to get the missing functional groups and stereocenters right. The synthesis continued as follows. First we have an epoxidation of the alkene because we need some oxygens up in here. Let's look at the strong diastereoselectivity again. Do you have any ideas? You might have realized that the epoxide forms on the side of our hydroxyl group. The free OH can coordinate to the vanadium catalyst and thus is another example of a nice directing effect. Now the chemists ran another, this time simpler Wittig reaction. This reaction has two motives if we remember our retrosynthesis. On one hand, we need an additional carbon here in our final product anyways. On the other hand, masking the ketone helps us achieve the unintuitive introduction of the other missing oxygen. You see, the next steps included SN2 opening of the epoxide with iodide and acetylation, followed by elimination of the iodide. This alkene will be used to introduce the missing hydroxyl group. The authors found that the analogous sequence does not work for the ketone. Not only does the olefin migrate from beta-gamma to the alpha-beta position, but we see another elimination due to the high stability of the conjugated system. We need to retain this precious protected hydroxyl group, so this is why the Wittig step was critical. To complete our target, we now have to tweak our free olefins. To install a tertiary alcohol up top, the chemists used a modified Mukayama hydration and in the same pot deprotected the acetates. This gave 53% of a single isomer, so again, we should try to understand the selectivities at hand. First, the exocyclic alkene reacts preferentially. This is not too surprising, given these are less stabilized and more sterically accessible than their endocyclic counterparts. What about the regioselectivity of the addition? Well, this reaction is initiated by an iron-free hydride catalyst which adds a hydrogen at the terminal position to create a stable tertiary radical. This intermediate reacts with the nitrooxidant and over the next steps regenerates the catalyst and cleaves off a nitroso byproduct. The only question left is the diastereoselectivity. Looking at the simplified model of the molecule, we realize that the cis-fused 5,5 ring is slightly bowl-shaped and more accessible from the convex or top face. Thus, the oxidant adds in a syn fashion compared to the hydrogens. After removal of the acetates, the C10 hydroxyl group was selectively oxidized with des-Martin periodinane. Then a methyl addition gave the second last tertiary alcohol. The last tertiary alcohol came from another Mukayama hydration. This time it was more standard, using O2 as the oxidant. To wrap up, we need to get rid of our two bystanders. The TBS protecting group was removed under acidic conditions, and finally, a radical hydrogenation gave Kalmanol with the correct configuration. 0.46% overall yield seems still low at first glance, but it's actually pretty good as it amounts to over 75% average yield per step. In comparison, the first ever synthesis of Kalmanol published in 2023 only gave 0.06% overall yield. Explaining this one in full would have required an hour, so you're probably happy that we picked the simpler synthesis. Here we come full circle on the primary mad honey toxin Grayanotoxin, as this synthetic odyssey devised a divergent approach to access both targets from a common precursor. Eager viewers can study this for some more crazy chemistry. But will this synthetic material really be valuable? There is a chance that this remains organic chemistry circle jerking, but maybe science will use these compounds to learn something new, as we've mentioned. Remember tetrodotoxin, which binds to site 1 of voltage-gated sodium ion channels? We can also look to its cousin saxitoxin, whose first total synthesis was achieved by Kishi in 1977. Decades later, fueled by new biophysical methods and smart synthesis, we are still gathering new insights into ion channels. Obviously, if someone wants to look at Kalmanol or other mad honey toxins today, it shouldn't take them as long, but any translation of this work will require several years at least. There's also a good chance that this research turns out to be not so useful. This is where we wrap up. Thanks so much for watching until the very end. Let me know how you liked this video and if you learned something new. I hope to see you soon in the next one. Until then, all the best.